In this video, we will illustrate how we can quickly and efficiently apply Newton's method via the calculator. So to begin, let's look at the motivating example. Newton's method is used to solve where a function is equal to 0, and we would like to use it to find the root or the solution of the equation x cubed minus 3x minus 5 equals 0. So just a quick reminder of Newton's method. We have the function we're dealing with. We need to calculate its derivative. And then we have the following, we might call an iterative scheme that allows us to come up with the approximations that we use for Newton's method. So we start off with a guess x1, and then we use the scheme above to get the next one. So I take x1 minus f of x1 over f prime of x1, and that would give me x2. And then I keep repeating until I get that desired level of approximation. So the first thing is, what should we use for x1? So if I come over here to my calculator, I've entered in the function x cubed minus 3x minus 5, and I see its graph. And it looks like its root is somewhere between 2 and 3 and closer to 2. So what I'm going to do is use 2 as my first guess. And then I'm going to go through and determine what is x2, x3, x4, x5, and I'll stop when I have 2 iterations in a row that agree to these 5 decimal places of accuracy. So I need to enter this xn minus the f of xn over f prime xn into my calculator in the y equals. So clear out whatever's there, and then we have x minus, and a very important thing when you're entering this is to use parentheses appropriately. So I'm going to put parentheses around this entire function that is in the top. So in the top we'll have x cubed minus 3x minus 5, and we are dividing this by the function 3x squared. So note every xn is just becoming an x minus 3. So the function in the top, the function in the bottom, I've put parentheses around both of them. I'm just going to hit enter, and then we exit to the normal window, so second quit. And what I'm going to do now is just enter my first guess. My guess for x1 was 2. And then what we want to do is evaluate the function that we've entered in for y1 at that point 2. And how we do that with our calculator is we go to the vars button, so vars for variables, scoot over to y variables, hit enter, and hit enter on the function y1. And I want y1 evaluated at 2, but to make this work really efficiently, what I'm going to do is evaluate it at second and then answer. So when you evaluate it at answer, what it's doing is taking whatever was the previous answer and it's evaluating it there. So I hit enter, and that's going to give me my x2. So 2.33333, and I'm looking for 5 decimal places of accuracy, so I'm going to stop there. And then the beautiful thing is, now that we've entered this in, when we hit enter again, it's just calculating another iteration. So that value we see in the next line is our x sub 3, 2.28055. I hit enter again, and we get our x sub 4, 2.27902. I hit enter again, 2.27901, and oh, we're almost there, because we want to stop when we get 2 iterations in a row that agree to 5 decimal places. And here we got it now with our x sub 6 is 2.27901 as well. And that tells us that our guess for x is going to be 2.27901, and that's correct to 5 decimal places of accuracy. So let's go ahead and repeat this process for a few more examples. So the next example is to find the positive root of the equation x to the 6 minus 2 equals 0. So we're going to go ahead and repeat this entire process. The first thing I'm going to do is clear out the function, and I'm going to graph x to the 6 minus x to the 6 minus 2. So enter graph. Okay, it looks like that positive root is awfully close to 1, so we will go ahead and use 1 as our first guess. And what we now need to enter in for the y equals is this iterative scheme we have for Newton's method. We have our function and its derivative, so it's x minus the function over its derivative. So in this case we will have x minus, and remember to be very careful with your parentheses. What's in the top is x to the 6th power minus 2 in parentheses, then dividing by, and I put parentheses around what's in the bottom, 6x to the 5th. Oops. There you go. Now I hit enter. I exit out of here. So I now plug in the number that I want for my first guess, x1. And now I need to get to that y1 function. So remember, we hit the vars, i.e. variable button, go over to the right for y variables, and hit 1 on function. And then we select y1. And I want y1 evaluated at that 1, which is really just second answer. So I hit enter. That gives me x2, 1.16666. I come over and I hit enter again. That gives me x sub 3, 1.12644. And remember, how long do we keep going? Until 2 iterations in a row agree for those first 5 decimal places. 1.12249. Oh, so we're almost there. Maybe just one more. Our next one, x5, 1.12246. Okay, one more. And here we are. X sub 6, 1.12246. And that gives us our approximation to the root of the equation x to the 6 minus 2, correct to 5 decimal places. And note, using our calculator, it almost seems too easy, as though it's doing all the work for us. But remember, we are the ones who have to set everything up appropriately in terms of what is the function, what is its derivative, what is a good initial guess. So let's look at another example. We want to find the solution of the equation cosine of x equals 2x. Now, this is not in the form we want for Newton's method. We want to apply Newton's method to find the solution of where a function is equal to 0. So what we have to do is subtract off that 2x. So the function that we use for Newton's method is cosine x minus 2x. Its derivative is minus sine x minus 2. So let's think about what will make a good initial guess. I want to graph the function cosine of x. So cosine of x minus 2x. And it looks like that solution there is somewhere between 0 and 1. So I'm just going to go ahead and guess 1 as the initial guess. Then we go back to our y equals, clear out the function that we had, and we need to enter in the quantity here. So the x minus, and then parentheses around what's in the top. So that would be cosine of x minus 2x, all divided by, parentheses around what's in the bottom, minus sine of x minus 2, and then an in parenthesis. So now we exit out of the y equals screen. We enter in our initial guess, so 1. We go to variables, y variables, function, select y1, and we want to evaluate this at the 1 that we'd have entered in previously. So second answer, enter. So our x sub 2 is 0.48628. Enter again. Our x sub 3, 0.45041. enter again our x sub 4, 0.45018, and we see every time we should be getting a little bit closer. Okay, our x sub 5, 0.45018, and we have 2 iterations in a row that agree for 5 decimal places. So that is our approximation to 5 decimal places of accuracy. So let's look at one more example of using Newton's method. So find the positive root of 2x squared minus sine x equals 0. So we have our function, its derivative, and we combine together for this Newton's method iterative approach. And let's go ahead and clear everything out, and we plug the original function in. So 2x squared minus sine, and this will give us an idea of what we should use for our first guess. So it looks like those solutions must be really close to 0. So let's go ahead and just use 1 as our first guess. And using 1 as our first guess is going to hopefully ensure that we get the positive solution if there is a negative solution there. So 1, and then coming over to y equals, we need to enter in our approach. So x minus, parentheses around the function in the top, so 2x squared minus sine, then in parentheses, divide it by, parentheses around what's in the bottom, 4x minus cosine. Enter. So we exit out to the standard screen. Our initial guess is 1, so we enter that in. Then we go to variables, to the right to y variables, select function, select y1, and we evaluate y1 at second answer. So our x sub 2 in this case is going to be 0.66513. For x sub 3, we hit enter again, 0.52229. For x4, we hit enter again, 0.48408. For x5, we hit enter again. Okay, now we're getting some agreement here, 0.48096. For x sub 6, 0.48094. So at least one more here. X sub 7, now we're good to go. We have that 5 decimal places agreement between x6 and x7, and that gives us our approximation to the root correct to 5 decimal places of accuracy.